Okay, so welcome back. It's Sunday morning, it's 9 o'clock. It must be lecture time. What I want to do in my last lecture is really talk about the two-dimensional border collision normal form, okay, which we had last time. It's the map in two parts, an F0 on the left, x less than 0, an F1 on the right, x greater than 0, and it's linear. So that, you hope, is a big, something that allows you to do calculations that maybe you wouldn't be able to do in a more general setting. Right, so there's going to really be three parts to this talk. First of all, I want to talk about some features of the periodic orbits, and then this idea of robust chaos. And there are two parts to this. One is quasi-one-dimensional attractors, where the attractor basically is a sort of a Cantor set of lines. And the second is fully two-dimensional attractors, where the attractor literally fills a two-dimensional region. Okay. And so I'm going to give this talk with a degree of trepidation, because if one was to put names to these things, the main ideas behind it were developed by David Simpson, there, with Jim Meese. And if I was to put a name to this one, I'd put Banerjee, and who's there, and Gambaudo and York. And so the only one that I feel completely comfortable about talking about is the last one, because that's what I was working on. So these two are going to have to forgive me at various stages. So the other thing that might be worth pointing out, the border collision normal form is a very natural thing. If you're thinking about looking at complicated dynamics in two dimensions, then trying to do something continuous, but which is linear, as I've said, linear means that you can do calculations much more straightforwardly. It's a very natural thing to do. So although in the context that we've been talking about things, this was around 1992, a paper by Nusser and York, that really developed the idea systematically, and that was followed up 1998, Banerjee, Gambaudo, who sort of really explained it in terms of why you'd be interested in it in a very clear way, linking it to applications. Okay. But actually, as I've already said, various aspects of it, the idea that a piecewise linear two-dimensional map would be interesting to look at predates this quite significantly. So Lozi map, which I showed you last time, which is an example of this, was 78. Lozi, there was a group around Christian Mira. So I think that was the mid-1970s, 75 plus, Mira and Laura Gardini, who still works in this area. We're already looking at this sort of map as a generalization of the one-dimensional dynamics. So actually, and I suppose I should put, in the 80s, both, I'll talk about their work, so I won't write them down, Mizierovic and Lysang Young were also working on these things. So quite a lot of work was happening on the border collision normal form before the border collision normal form was invented, or at least recognized as such. So it's one of these areas where it is such a natural object that different people at different times have looked at it. And this makes actually studying it sometimes, I mean, certainly when I started looking at these things, really quite confusing, because you come across one thing here in sort of the early 2000s, and you realize that they don't realize that there's this stuff from the 1980s or even from the 1970s. And the whole area has been developed in different ways in different places. Not criticism of anyone, it's just that's the way, if you like, that one develops ideas which are very, very natural. So, that's where we are. Periodic orbits, quasi-1D, fully 2D. Fully 2D is, I suppose, you know, if you were trying to think about what we were doing before, the periodic orbits is very much about sort of trying to understand the bifurcation structure. So this links with the bifurcation analysis that people like Victor do, and which you've seen for the one-dimensional cases. This actually links to something that we haven't really talked about, but there was a very, very well-developed theory by the, I guess, mid-1970s of the transverse intersection of stable and unstable manifolds of fixed points and Newhouse phenomena and things like that. So this provided something, again, where people could actually show things were happening in a very explicit way, and which had some quite interesting twists that are different from the smooth systems. And this is an area where, again, the first examples of this were based on the Markov partition ideas that we've talked about before. And just on that, I had a sort of bet. There's a mathematician called Tureyev at Imperial College, but who had worked with the Shilnikov group, and he didn't believe that the fully two-dimensional attractors would be possible. So he said, you know, even if they happened at one parameter, if you perturbed it a bit, you'd get holes in it and it wouldn't be fully two-dimensional. So he and I had quite a long period of sort of iterating. So he said it's not possible. I said, look, I've got an example. He said, well, that's an isolated example. And it sort of went on like that. Right. So this is where we were. And there's the Lozi map and the Henel map again. Just again, this thing of making the square piecewise, linear, simplifying the calculations, because now you've got a linear composition of linear maps. Here you've got a composition of nonlinear maps, which is much harder to deal with. Okay, and I won't do that. So I guess, Soumitro, you showed some of these sorts of things. So this is from Banerjee and Gambaudo in 1999. I apologize for the quality. But what they started by doing, so you have this map, you've demonstrated that it's interesting from a physical point of view. Okay, so there were electric circuit systems where analysis of this map would be interesting, and that you knew that it was a normal form for some bifurcation theory. But what happens? So what's the phenomenology? Sort of, you know, it's in principle interesting, but is it dynamically interesting at the same time? So the first thing is, let's establish that it's dynamically interesting. So what this is meant to show is that you can get a transition. So this is the parameter, 4 different pictures, and they actually had rather more. I can't remember whether I think I do have the next set too. So this is going from nothing, there's no attractor, to a stable fixed point. This is no attractor to stable chaos. So we've got X here. This is stable fixed point going to chaos. This is stable fixed point going to stable fixed point. Keep going. This is more complicated. So I'm going to have to read the thing. So 4 is a coexisting fixed point of period 3, so that's the fixed point. And then 1, 2, 3, so you're cycling through that, and that's the fixed point. 2 coexisting fixed point, and period 4. So out of the period 3 somehow, and the fixed point keeps going, and period 3 goes to period 4. This is sort of a classic doubling type of thing. You've got period 1 going to period 2. Here, looks as though you've got period 11 going to period 2, and here's a fixed point to coexisting chaotic attractor and an orbit of period 5. When they published this sort of thing, or this paper actually, these sorts of transitions were utterly unknown. Okay, you just hadn't seen that sort of thing. So it was as though a sort of a complete new sort of set of possibilities arise, and the questions are, which bits can you understand? Certainly, it's not the case that we understand everything that happens in the order collision normal form, and I've mentioned before my less is more mantra, that actually what this shows is that all the possibilities are incredibly complicated. So the question then is, what do you try to do? Do you try to write down all the possible diagrams that I could get here, or do you try to pick out some organizing ideas and concentrate on those? And through these three things, what I'm trying to do is, in a sense, pick out certain organizing ideas that you can use to start to understand more specific things. Okay. Now, whenever you have an ordinary differential equation or a map, first thing you do is look for the fixed point. Do the easy bits first. Again, I hope that's sort of something that's come across in these lectures, that you don't try and do the hard bit before you know the easy bit. Okay? So things you can do is look for the fixed points, and I'm not going to go through this, but just to show that you can. So you get some equations, and there are some conditions you need. If you're looking at F1, you need the x to be positive. Okay, so you have to keep looking at that sort of criterion to see what happens. You can do the fixed points in x less than 0. You can work out when the two branches are on the same, occur for the same sign of mu, in which case you have two branches, one in x greater than 0, one x less than 0 that come together, or when they're on opposite sides of mu, in which case one comes in and the other one goes out. And you can look at the period 2. I mean, it's a linear system. It's just linear equations. So you can look for period 2, and you can find conditions, and in the end you say, so what? Okay. You've done the period 1 and period 2, but we've already seen that there's a huge amount more than that. Now, that's not to say you shouldn't do this. Okay, absolutely, this is the first thing you do. But where can you go from there? So there are certainly other periodic orbits, and and the work by Laura Gardini and others had started to sort of give a good sense of bifurcation structures. What David did, I guess your thesis, was to produce a systematic approach which allowed you to understand some of these, some features without having to go, to some extent in great detail, but equally just to understand the principles that were going on. Okay. So I'm not going to go through the detail. These notes will be available next week or something, so if you want to look at the detail, you can. Just to say that it's a bit similar to some of the manipulations you were doing with the normal form in some ways earlier this week, that if you look at the nth iterate, it's some matrix type, it's a composition of linear maps, or strictly speaking, affine maps, linear plus constant maps. And if you compose linear maps, you get linear maps. So you then ask, well, I've got a matrix MS. Well, MS is, you started somewhere, and so you've got those, if you think about the normal form, it's a matrix plus a constant. So the matrix could be A0 or A1, depending on which side you are. So given a sequence of being on the left, being on the right, you can write down that matrix. The P's come by looking at the constant terms. And you can sort of then, formally at least, write down what a fixed point would look like. This equals x. So here, formally, we've solved this equation, but we don't know yet which possible sequences of s's give me something that means anything. Okay, and also we need a non-singularity condition. So, so far, this is, if you like, just saying, well, in an ideal world, this is what I'd like to solve. So the question becomes, what can I do with this? Okay, there's nothing, this is just linear algebra. The smart thing is to be able to say which side of the border, the switching surface, are you on at each stage, and so you get a whole set of consistency conditions to say whether this actually exists for the border collision normal form. Because this just says, I'll put together some sequence of s's, some choices of being on the left, being on the right, being on the left. I end up with a linear equation, which I can solve in principle. I can write down solutions. But that doesn't tell me that when I applied F0, I was on the left, and when I applied F1, I was on the right. It simply says, I'll apply one, I'll apply the other, I'll apply that one, I'll apply that one. And it doesn't check whether you've got consistency that you would need for this. And in fact, I mean, it may be worth pointing out that there's a whole other industry of what are called iterated function systems, where you have, in the simplest cases, you take some set of linear maps, okay, and then you just apply them at random. So you take a point, choose one of your linear maps, hit it. Apply, choose another of your linear maps, hit it. And so you're applying randomly each step some choice from some finite set of linear maps. And in some ways, at this stage, that's all we're doing. Yep. Yes, exactly. So when they're contractions, when all the linear maps are contractions, you get a beautiful fractal structure, self-similar sets coming in, and that sort of thing. So if you think about taking the border collision normal form and not saying I'll apply one on the left and one on the right, but just I'll apply one, then I'll apply the other, and then I'll apply that, then that's what we're playing here. And you can see now the subtlety for the border collision normal form, and the thing that David and Jim Meese managed to sort out was, I want to go from just saying, oh, I'll choose some sequence of lefts and rights and I'll apply those maps, to saying, right, I'll do that, but then I will go back and I will check whether they were on the right side for the border collision normal form, to be consistent with the border collision normal form. Okay, so that's why this, if you like, is just formalism. All I've done here is I've said, well, choose some sequence. Well, I can write down the equation, and here it is. But at the moment, I have. So if now I was going to say, think of this as an iterated function system, I could say, well, if I now choose to repeat this sequence, then this would be a fixed point. It really would be a fixed point. Okay, but at the moment, if I think about it in terms of the border collision normal form, I have no idea whether this means anything at all, because the third point might be on the wrong side for the map that I've applied. And so there's a whole set of things that you have to check. And that was what was, I'm not going to go through this, it'll be in the notes, or you could be much more sensible to read David's papers. But you can work through it. And what you find is this really interesting picture. So this is two parameters. Okay. And the different colors are different periodic orbits. Okay, so here's a periodic orbit, and it exists in this region of parameter space. And then the orange one exists in this region. Then this sort of slightly yellowy orange one. Moving forward. And this has really interesting features. It seems to have this pinching point here. And you can sort of see that what's happening in each of these looks similar, except the number of lobes is increasing as I move that way. Okay. So, to some extent, what David did, Jim did through sort of their calculations with the linear form, which I will say, hang on, do I have it here? No, I don't. I haven't used that. Okay, so I won't say that. Is to start explaining why you get these structures in parameter space. Okay, and those are the parameter values if you want them. So this, and again, I apologize for the, maybe I'll draw a bit of this. So the basic, let's just do it. The basic story is that when I have a periodic orbit, I can have, so the point is, this is meant to be indicating a periodic orbit, and here's the boundary. This is x equals 0. Okay. And if you imagine what happens as you change parameters, these points move around. And you get a border collision if one of them hits the border. And so this left-hand side here is where that point there has hit the border. So it's, and if you look at it, it means that this point has come to the border here, and this point, so you've got two, it's like a sub-node bifurcation. This point has come to the border here, this point has come to the border here. So if in other words, if I take this picture and perturb it a bit, two periodic orbits are created, one where this point has gone left and one where it's gone right. It's a 7-node bifurcation. On the other side, it's one of the upper points that has hit. Have I got that right? And so, yeah, so upper point has hit, and now, sorry, and that means if I perturb that, the 7-node bifurcation, one point goes to the left, making 3 on the left, that's that one, and one point goes to the right, the other one goes to the right, the 2 on the left, which is that one. So it's analyzing the 7-node bifurcations here. What you find is they cross over, and the crossover changes the proportions on each side. You see, here you've got 3 or 2 on the left, here you've got 4 or 3. Okay. And that structure then repeats as you move down the chain. Okay. And essentially, summary is, without going through the detail, is that you get these lobes, and at the shrinking point, there's a degenerate invariant thing with 2 points on the critical line. And this beautiful structure does not persist for typical nonlinear perturbations. Okay, and there's a natural unfolding, which Simpson and Mies also looked at. But the point is that in the linear system, I mean, so the moral of this is really that by doing a certain amount of linear analysis and thinking about the geometry of these orbits, you can understand this structure. And so the number of lobes become the number of different ways you can have things on the left and the right interacting. Okay. And they're effectively acting like rotations, but I don't want to go into that. Okay. So I think that's right. So I'm just going to change the file. Right. So you can also ask a question, how many stable periodic orbits you can get, coexisting. How many stable coexisting orbits can you get? Now we know from smooth theory that there are phenomena called infinitely many sinks, where when you have a homoclinic tangency, so this is where, and this will come in a bit with the robust chaos, So suppose you have a fixed point of the map which is a saddle. So things are moving away along the unstable manifold, they're coming in along the stable manifold. Okay. So you can have a homoclinic connection, which means a connection which allows you to leave here and come back along here. So typically what you get is what's called a transverse intersection. So this point is on the stable and on the unstable manifold. So if I work backwards in time, it goes back down here to here. And if I go forwards in time, it goes into there. So I have a discrete set of points that approach from one side and from the other. And this is another transverse homoclinic intersection. But if you think about how you make that by changing parameters, there will be, and homoclinic orbits, I mean, David mentioned the Shilnikov type of thing for the continuous flow. Homoclinic orbits are often very good organizing centers, interesting bifurcations. So how do you create, as you change parameters, a homoclinic orbit for a map in 2D, is you have a tangency. Okay. And in the early 1970s, Sheldon Newhouse proved that if you perturb this situation a little bit for a smooth system, then there will be parameters where you have infinitely many stable periodic orbits. Okay, which is called Newhouse phenomenon or infinitely many sinks. So in the smooth case, we know that you can have that associated with homoclinic tangencies, you get infinitely many sinks. So is there anything similar going on here? So Laura Gardini had shown that there were very complicated regions of multistability in the border collision normal form by effectively numerical methods, but David again showed that there are parameter values for the border collision normal form at which there really are infinitely many stable periodic orbits. And this is a very nice picture from his paper where you can see different colors correspond to different orbits of larger and larger period accumulating on these three, or some points on the orbits, accumulating on these three periodic points. And the stability of these 3 points is quite interesting because although they're saddles, it's area preserving locally at that. The determinant of the map, the third iterate of the map here, is 1. And so one of the principles I hope that you're starting to see in this is none of the things that we're talking about happen on their own. And none of the things we're talking about are isolated phenomena. They're all connected. So an interesting point here is that Jean-Marc Gambaudo and Charles Tresser in 1983 had also constructed a piecewise smooth map without knowing that there was a theory of piecewise smooth maps. They were just doing it where basically they took the square and the image of the square, imagine the square had horizontal lines, and now you take the image of the square and you compress it and stretch it and then put it back down so that the horizontal lines are like this, but then you bend it here and then you put it down so the horizontal lines are still horizontal. So it's a bit like the Smale horseshoe, except that the bent bit doesn't go out of the top of the box. Okay. And this is 1983, remember. In 1983, we did not have access to the same sort of computer power as they did now, as you do now. So they were in Minneapolis, the institute there, and so they found an example. Here's period 2, here's period 3, here's period 4, And they were able to prove that for their piecewise smooth map, there were infinitely many stable periodic orbits accumulating, or points on them all accumulating on this point, which is a saddle. This point is a saddle with eigenvalue lambda in one direction, mu in the other, so you've squeezed and you've expanded, and the product of those is 1. So once again, this is area preserving. So they were doing this because although Newhouse phenomenon had been around for sort of 10 years odd, there had been no explicit example where people could say, here's the Newhouse phenomenon working. Okay. And what I think is interesting, and which I have no idea whether it's, I mean, I suspect I have a sense of why this is true, but all the simple examples that we have, the two simple examples that we have of this have this area preserving property and have been invented completely independently. So again, I think there's an interesting thing here about looking at the infinitely many sinks property in piecewise smooth systems and asking, what is it about, is it the two examples that we have, what's the general theory for that? Okay, at the moment, there's no general theory, as far as I know. There's sort of well-chosen examples. Why is this local area preserving so important? And you can sort of see it. So one thing about area preserving maps is that they have what are called islands of stability, and there's a sense in which you see this as an attempt to make use of that. Right, I don't want to do that. I'm not going to do that. I want, yeah, robust chaos. So am I on the last one now? Right. So now we're coming to Soumitro stuff. So, as I said before, the intersection of stable and unstable manifolds was a classic part of the development of the ideas of chaos. So the homoclinic tangency and transverse homoclinic orbits was one of the first places where it was proved that you could have chaos in some sort of general setting. So the existence of the existence of chaos due to to transverse homoclinic intersections was one of the standard examples. In fact, it pretty much goes back to Poincaré. So writing in 1892, you get the feeling that Poincaré, so he was trying to describe complicated dynamics associated with certain types of periodic orbit, and he sort of had the idea of what we now call a Poincaré map, of taking a return map to a Poincaré, which is now called a Poincaré map, to a periodic orbit. And he has there's some little snatches. This is in Méthode Nouvelle de la Mécanique Céleste, new methods for celestial mechanics. He had some really interesting little side comments that if certain things happened, then things would look very complicated. It's really hard to tell how much he sort of knew about this. But let's just, if we just take this picture and take the transverse case. So again, it's this principle that nothing is new. So suppose that I have that sort of situation. I have transverse intersection of the stable and unstable manifolds. Well, if I go forward in time, these points map to discrete points down here, which means that this curve has to keep intersecting here. Okay. But now we're getting close to the origin, which has stretching along here. So actually, we're starting to get, as well as accumulating down here, we're starting to be stretched along here. Okay, and that structure is going to continue. But the same is true in backwards time. In backwards time, this point goes here, here, back, back, back. So these sort of things have to do, now I'm coming around here. They're going to do something similar backwards in time, but now backwards in time, this is stretching. So I've got to start stretching. Whoops, I'm going the wrong way. And so on. And this is called, in great technical detail, a homoclinic tangle, because it's all tangled up. Okay. So this was a sort of standard picture in the smooth case. And it's this tangling, it's this stretching, this combination of stretching. What you can then do is prove that there are regions in here which come back stretched across themselves, and you can prove the existence of smell horseshoes in the dynamics. Okay. And to some extent, what Banerjee, Grogi, and York did was spot that in the border collision normal form, you have homoclinic connections, transverse homoclinic connections. Okay. But there's an extra thing that they noticed. In a sense, this was, so I think, no, spotting that there were transverse homoclinic orbits is not particularly deep. The thing that they noticed, which really sort of makes the difference, is that these created attractors that were persistent. So chaotic attractors that were persistent. Okay, so you have two things. You have the idea of a homoclinic intersection, which is completely classical. But in the classical example, the chaos that you produce is not stable. It's a collection of saddles. And typically you don't have attractors. Well, that's not quite true. You do have attractors, but they're sort of flitting in and out, so you're getting bits of stable periodic orbits and so on. It's a bit like the logistic map. If you think about these places where things turn round as being areas of local contraction, because things are being brought together by the turning point, then you can imagine it being a bit like the logistic map, and that gives you contraction, which gives you stability. But it flits in and out. It's changing the whole time. The thing that Soumitro and Celso and people noticed, and this was really the important thing, I think, in this paper, I mean, it's sort of crucial, is that in the piecewise smooth case, you don't get this attractor not being attracting blah, 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 blah complication. But over ranges of parameter values, you have a chaotic attractor. Okay, it's changing. The precise dynamics within it is changing as you change the parameters. But the existence of the chaotic attractor is persistent. And this is utterly different to the smooth case. Okay? And it means that the piecewise smooth systems have this robust property, in a sense, simplification, and this is going in the opposite direction to most of what we've been talking about. Most of the time we've been talking about the non-smooth, the piecewise smooth having greater complexity. Now, so you can then ask whether it's more complex to always have a chaotic attractor, because chaotic attractors are complicated. But in a sense, conceptually, this was one of the first cases, I think, where you suddenly saw that the piecewise smooth systems were conceptually easier to deal with in certain ways because they had persistent structures. So things that within the smooth world were not persistent, you varied parameters a little bit, and you got a stable periodic orbit, you got something else, you got blah, blah, blah. In the non-smooth case, the piecewise smooth case, you got a persistence of a strange attractor. So they call this robust chaos. Okay. There have been papers since then claiming things like robust chaos for smooth systems, But if you look at the detail of those, nearly all of them do a little trick. What they do is say, I'll set up a family of smooth systems, and if you look carefully at that family, you find that actually they're all topologically conjugate to each other. So what you've done is you've said, right, so suppose that I said, I'll find a chaotic smooth map. And now I'll think of a whole smooth family of coordinate transformations. Okay? And now I create a new family of maps by coordinate transformation of my chaotic map. Oh, look, all those family of maps are chaotic. And so the chaos is robust. Well, frankly, that's not surprising. You've set it up so that that's the case. But if I'd made a perturbation in an arbitrarily close to that, if I'd made a different sort of perturbation, I would have got something not chaotic. And this is something that Sebastian van Strien proved, I can't remember quite when, that for typical one-dimensional unimodal maps, for example, I mean, his work's more general, for typical ones of those, the attractors are not persistent to typical bifurcations. So it really is that the remark that Soumitro, Celso were making is really absolutely a feature of the piecewise smooth world. Okay. So what happened? So the two very nice papers, 1998 and 1999, setting this out. But both of them were in physics journals. There wasn't complete, wasn't a complete, quotes, mathematical theorem proof type of thing at all. But it demonstrated the phenomenon and, again, introduced this idea of this robust chaos, which I think is an incredibly important feature. And again, it's that sort of thing, sorry, I sort of feel I'm repeating myself, but there are various times when things happen when the real power of what somebody has done is not the actual thing that they've done, but recognizing the implication of what they've done. And I think, if you think back to that story I was saying, talking about Ed Lorenz, noticing that when he re-put in the numbers, he got something different. He didn't say, oh, well, so what? I'll just go with the latest run. He actually thought about what was going on. And I think the same thing with the robust chaos. It's not, oh, well, I can do this little proof, but actually, this is important, this is different, and this is not what we're expecting from our smooth theory. Okay, so take of that. So what you can do, so here's a little sketch of the type of thing that one gets. And what we have here is we have a fixed point. So we're trying to do, if you like, two things. I'm trying to think about how I can describe what's going on. So I have a fixed point here. Okay, so this is, and the fixed point has a stable manifold and an unstable manifold. So here's the switching surface. So what I want to do is just describe briefly how you build up this sort of picture. So X here is the fixed point. It's got two real eigenvalues. One of them is unstable and negative. So things are oscillating. So on the unstable manifold, things are oscillating from side to side. On the stable manifold, I've got an eigenvalue with modulus less than 1, which is positive. So things are coming in from one side or from another. Okay, so negative eigenvalue means that each time that you apply the map, you flip sides. Positive eigenvalue means that you stay the same side. Okay. And so, what are the bits that matter? Remember that we've got this boundary here, and the map on the right, we can only apply on the right. Well, for the stable manifold, I've got T here. This is where the stable manifold intersects the boundary. So I can't extend it further here, because here, I know that I come down towards X, but if I'm here, I don't know where I'm mapped to. So the stable manifold cannot be extended beyond here. Now let's look at the unstable manifold. The unstable manifold intersects that point, intersects the x-axis at z. Now the image under the border collision normal form of the x-axis is the y-axis, which is the boundary. So the image of z, remember it goes on the other side. So here's, sorry, I've got that the wrong way around. The image of the y-axis is the x-axis. So take this point, so I've gone for the wrong point. This point here will map to the x-axis. So it will map here. This point here will map on the same line, because it's an eigenvector, will map onto the same line, but further away than here, because it's unstable. So it will map somewhere up here. In other words, the whole of this line here, under the map on the right, will map to the whole of that line segment there. Okay, x, z maps to x, f of z. Okay, under the map. So this whole bit, including the bit in x less than 0, is part of the unstable manifold of the point x. Okay. So now I want to start to try to build up bits of this picture. And I also want to do something else, which is to say there's some sort of invariant region. Right, so here's fz. We haven't thought about the left at all yet. So now let's apply the map on the left. And let's suppose that the map on the left takes z, f of z to here, and then at the next iterate, it's here. Okay, so for typical, this is not unusual. It's the sort of thing that happens. Okay, so now let's look now at this triangle here. Okay. We want to know where bits of it go. So we've got two, this triangle actually splits into two parts, a quadrilateral on the left and a triangle on the right. Now S is on the y-axis, the boundary, so it will map to the x-axis. It's on the left, the way I've drawn it, it's on the left of this line. So because it's flipping backwards and forwards, it will be on the right of it, its image will be on the right. Because it's stable in this direction, thinking about the right-hand map, its image will be closer to x, and it will be on this line. So it will be on the other side of that line, and closer to x, so it must be something like there. Okay, so exactly where it is doesn't matter, but it's going to be somewhere like there. So now, let's look at the image of, say, that triangle. Well, z goes to f of z. F inverse of z goes to z. S goes inside. So zs goes to this line. Okay. So that line goes to this line. Okay. And then what about this bit? That's between z and f of z. Well, that goes to f of z and f2 of s, which I haven't drawn. But what you can see is provided... Sorry, that's not what I'm trying to do. I'm trying to get this. So what have we got? Sorry, this is where you have to take it slowly. So this line, we've said, maps to that line. This line maps to f2 to z f of s. That's what I was trying to do. That's the line I didn't do. This line here, remember, under piecewise, under linear maps, straight lines map to straight lines. So this map, if I know the endpoints, I know where they go. F inverse goes to there, z goes to there, this goes to there, so this goes to there. Okay, and then zs goes to f of z, f of s. So in other words, that's where I've got it now. This triangle maps to that triangle. Okay, we with that. Now I do the same here. So f of z, so I've got now 4 lines to worry about. F of z goes to f2 of z, f inverse of z goes to z, so that goes to this line. So that deals with that bit. So let's go round it. Fz f2 goes to f2 f3, so that line goes to this line. So providing f3z is inside this triangle, it's inside the triangle. And now we've got that line. So f2z goes to f3, z goes to f of z. So this line goes to a line from f3z to f of z, which is inside the triangle I'm starting with. And f2z f of s goes to this line, which is inside, and the final bit, which is that we've talked about before. So basically, all the lines, the 4 lines here, all remain inside that big triangle. So what I've done, and I apologize if I've been confusing, but you can see the sort of argument you have to make is show that if I start within that triangle, if I'm in this triangle, I'm mapped inside the triangle. If I'm in that triangle, I'm also mapped inside the triangle. And so the triangle is invariant. Okay. And the crucial thing to make that work was that f3 of z lies inside that triangle. So that's, if you like, a constraint that I have to check. But we've also, as we've been doing this, to some extent, been creating other bits of the stable manifold, images of the unstable manifold. Images of the unstable manifold are on the unstable manifold. So this map to there. What about this bit? This is a bit of the unstable manifold, f inverse z, fz. Well, that maps to z, f2 of z. So this piece, z, f2 of z, is also a piece of the unstable manifold. And look, we've got a point P, which is an intersection of the unstable manifold and the stable manifold of this fixed point x. So we have, as I've drawn it here, a transverse intersection, which tells me that I have chaos. You then have to work really quite hard to decide. So we know we've got an attractor, and we know that we've got a transverse homoclinic intersection. The work then is to use that to show that you've got a chaotic attractor. And it's not completely clear. I'm going to have a pause. And I'm not going to go through the detail of this, but you can create the trapping. So I've talked about the trapping region, and so we've done that. And so you can then work out, you remember I said the condition was that f3 of z is contained in the triangle. You can then, at least for the Lozi map, or for any map actually, you can write out exactly what those conditions are. So the numbers aren't important. The point is that you have a simple geometric condition which you can translate very easily into an algebraic expression. And I guess I'm not going to go into the detail of any of this, but if you take a moral away from this is that whereas in the one-dimensional case, we were nearly always just dealing with conditions and where do things go and what almost all was analysis. Here, we've ended up with a geometric statement, okay, that we've gone, and I've spent a long time on that picture because I want you to get a feel for the types of argument one makes, that you move very much from an analytic thing to a geometric thing, which then turns out to have a geometric, so here's my condition for the trapping region, is that f3 of z is contained in the triangle, and then you calculate what that means. Okay, so it's a case of going through what's the geometry, how do these things fit? But then there are all sorts of assumptions I've made here. I've made the assumption that t is below s, for example, in order to have that point P there. If t was here, how would that change the picture? Well, maybe I've got an intersection here. If T was here, can that happen? Because then I wouldn't have an intersection at all. So you have to start thinking quite hard. I don't want to go through this. So there's a whole load of stuff that you can do. And actually, what was rather nice is, as I told you last time, Misiewicz in 1980 had done a very detailed description of the Lozi map based on this. And what he'd done in great detail was show that the Lozi map, it's the closure of the unstable manifold of X, which is what Banerjee and Gupte had done, and that the map is topologically transitive on this set, okay, which means that the whole set is part of the attractor. What I want you to notice is 1980. Okay, so again, it's different communities doing different things at different times. And what you want to be doing is to sort of take these things. So in some ways, this 1980 paper answers some of the questions posed by the 1998 paper of Soumitro and Celso. So I'm not going to go through the proof of that. I also want to just point out that Lysang Young, so Lysang Young is again one of the really big figures in ergodic theory applied to dynamical systems in the previous century. She's still alive, working very well. So she got interested in these piecewise smooth systems too. And she got interested in the piecewise smooth systems because she was stuck on doing things for the smooth systems. Again, it's that thing that we have much more uniform expansion here. And she had a theorem, which I won't go through, but basically I think that's, again, look at the dates. All these dates are sort of higgledy-piggledy because everyone's doing things for different motivations, publishing in different types of journal. Nobody knows what each other is doing. So Young proved the existence of chaotic, so it's just technical in some ways for chaotic, maps under certain hypotheses. And you can actually then, so again, I want to have a pause and then do the last bit. Numerically, you can check where her hypotheses fit with the blue region is Banerjee and Gupte. The colored regions is where Lysang Young's conditions for, now we've got extra information, we've got invariant measures, we've got nice structures in those regions. Okay, so I'm going to do the last 25 minutes on two-dimensional attractors, and so let's have a 5-minute break, and then we'll pick up till the end. Okay, so we'll start at 5 past so that I know what to look for on the clock. Okay, so should we do the last 25 minutes? Right, so I'd like to start with a picture which certainly makes it look as though you've got something that's filling up some polygonal area. Okay, although it's not completely clear, there are sort of bits here where it doesn't look very dense, and it's not quite clear what's happening. So Laura Gardini and people had proved the existence of two-dimensional absorbing regions, but we've done that already. So our triangle was a trapping region, an absorbing region, it was a two-dimensional area. We knew the attractor was inside there. They'd looked at the evolution of these regions, and also they'd analyzed, there are some cases where iterates of the border collision normal form decouple so into one-dimensional maps with discontinuity. And what they'd done there is they showed that in the y direction you had a one-dimensional map which had a whole interval as the attractor. In the x direction you had a one-dimensional map with the whole thing as the whole interval as an attractor. And so the claim was that if you take the cross product, you get a full region. Okay. A very, very interesting, but I still don't understand it, Dobrinsky in 1998 proved the existence of a 2D attractor in the same way that we've been talking about here. Okay, as the closure of one-dimensional unstable manifold. So you now imagine that instead of having a one-dimensional manifold that sort of starts to have this sort of structure, this actually fills in, it's still one dimension, but it's dense in a two-dimensional region. Okay, and so therefore the closure of it is a two-dimensional region. So the really interesting thing about this one is that it's a natural extension of what Soumitro and people did, where you still have the sense that the attractor is the closure of an unstable manifold, which is a one-dimensional set, but it's now fully two-dimensional. Okay, so what I did is different. Okay, because although if this is true, I think this could be really interesting. I think there's something very interesting going on here which I don't understand. Okay, is that transition from being a Cantor set. So typically, the sort of things that Soumitro created were, you can think of as a cross product of lines, the unstable manifold, and a Cantor set. So you take a cross section of that, you get lines on the Cantor set. Now suppose that the Cantor set gets so you lose more and more and more of the gaps in the Cantor set until you're dense in a 2D region. So this is the natural extension of the quasi-one-dimensional attractors, so quasi-one-dimensional in the sense that they're a one-dimensional cross a Cantor set locally, to a fully two-dimensional region. And so it's a bit like, I mean, anyone who does mathematics as an undergraduate comes across what's called a piano curve, which is, so the question that you ask is, if I have a square, how do I draw a line in it that is dense and doesn't cross itself? Okay, have people come across that problem? So it's one of those things where you start drawing it and then you find that, oh, you've done something and you can't get back into here. You have to keep getting closer and closer and closer to every point. Has anyone played that game with snakes where you have to, your snake grows as you, it's the same sort of problem, is that after a while, your snake doesn't have the room to sort of move. So this, I think there's something really interesting going on here. The way I approached it was different. What I said was, well, everyone's been talking about attractors involving stable, unstable manifolds. How about if on the right-hand side, and this is true of this picture, on the right-hand side, everything is an unstable manifold. So I have a complete, I don't have saddles, I have an unstable fixed point here. So it's expanding in all directions. Okay, so that means I don't have stable and unstable manifolds because I only have unstable manifolds. How does that simplify things? So the basic problem, two-dimensional attractors clearly exist in open regions parameter space, but what techniques do we have to prove them apart from what Laura Gardini and people had done, where it was essentially make it one-dimensional, a cross-product of one-dimensional maps. Okay, so the idea is Markov partitions. And a locally eventually onto, remember that was one of the expansion type properties. You have to be a little careful about this because you need to be able to show not just that you have chaos, but that you have chaos that fills a two-dimensional region. Okay, so I defined something called affine locally eventually onto, which is easier to control, but let's not worry about that. But you can choose, so here's the sort of thing that you can do. Remember when we did period 3 implies chaos, we had a sort of, we basically said we had period 3, and then we used that period 3 to construct a Markov partition. So here I've done something slightly more complicated. I've taken the origin, so I've chosen, so that the product of the determinants is negative, and the image of both the left half plane and the right half plane are in the lower half plane. So I've taken those, I've folded them, and I've put them back like that. Okay, and now I've said, can I do the following thing? Can I make 0 go to p? Well, that's easy because the image of 0 is 1. I mean, if you think about it, it's the constant bit. And the way that we've parameterized the border collision normal form, the constant bit is just the vector 1, 0. So p is just 1 on the x-axis. So that's not a problem. P goes there, then it goes to q, then it goes to r. Now on r, we're on the x-axis which goes to the y-axis, so let's make the r go to s here. Okay. Right, so that gives me a polygon. And now let's start thinking about where various things go. Now, so I've got this point Q. I don't want to make things too complicated. So I want to reuse some of my points. So the question is, can I make S go to Q? So send that to there. So both P goes to Q and S goes to Q. And of course, because I've folded, that doesn't contradict anything. Okay. Well, if I can, then I've got this line here. And I'm trying to create a Markov partition amongst the various lines I've got here. So let's think about this. I've got a point here. I've also created Q already exists, PR that already exists. So suppose that W goes to V, which lies on the y-axis, and V, because it's on the y-axis, goes to the x-axis. Well, can we make it go to 0? Okay, so it looks as though I've got quite a lot of conditions going on here. But I've also got a fair number of parameters in the border collision normal form. And if you actually add up how many of these are actually parameters, because 0 to P that's nothing. P to Q, that's nothing. All I'm saying is that Q is on the right still, so that's an open set of parameters. Q goes to R, well, that's something, because I want R to be on this, so that's one condition. I'm saying R, the x-coordinate of R is 0. Then R goes to S. Well, that's automatic that it's on the x-axis. So all I'm asking is on the left, and that's an open condition. So I've not added to the conditions that I'm doing. S going to Q, woo, that looks like 2 conditions. Because I'm saying each coordinate has to map in the way I want to do. And then I've got a bit more here, that's 1 condition, and that's 1 condition as well. So it looks as though I've got 5 conditions. But it turns out that you can, and if you think about the border collision normal form, I've got 4 natural parameters. It turns out that you can actually do this. I can't remember which one looks nastier than it is. But what this means is, once I've got this, if you take any of the triangles that I've got here, or even the quadrilateral there. So this point is on the intersection of OQ and PR. Okay, that's that point. So if you look at it, then its image must lie on the image of OQ, that's PR, and the image of PR, which is SQ. So it's W. So the image of that point, which we haven't really thought about at all, is naturally W and doesn't give me any extra things to worry about. Now what it means is that all the endpoints of my things, I know exactly where they go, and they go to the endpoints. So I've constructed a Markov partition. Now that on its own is enough to tell me what the dynamics is, but not enough to tell me that the attractor is fully 2-dimensional. Because I could have structure inside here with that dynamics. So in order to show that it's actually fully 2-dimensional, what you show is that for every sequence, anything in here is homomorphic, well, is to get to somewhere interesting, only uses a certain number of words. and that on those words, the map is completely expanding. So expanding in all directions. And therefore, that any iterate that's allowed by this uses combinations of so many on the left, so many on the right, so many on the left, so many on the right, and so on. That those combinations are completely expanding. And so the total thing that you've got is completely expanding. And that tells you that any little neighborhood expands in all directions, not just in some. And that gives you enough to prove the asymptotically locally eventually onto property, which then proves that periodic orbits are dense in the region rather than dense in particular subsets of the region. Okay. So that's an application of Markov partitions in 2 dimensions. And once you start getting this idea, then you can get a bit more sophisticated. So this is an example with a PhD student, Ivan Wong, from, I guess, 2011, 2013, I can't remember. So we've got a completely unstable fixed point here. So can we use that in a natural way? So the other one was, the previous example was done by saying, oh, I want things to sort of fit together in nice. Here, we've got a fixed point. So again, this point goes to this point, goes to this point. That can do n times around here. So the advantage with this is I'm now trying to get a countable number of examples, because Ivan Turev was saying, well, you've only got one example, that's not enough. So here I'm going to make a countable number of examples, because k can be anything. So basically I've got these number of things, and then I do the same sort of thing. AK goes to, that was my point S before, and now instead of taking, remember in the previous one I took this point to somewhere on the boundary out here, I'll take it to X star. Okay. This point automatically goes to there by the construction. And so I've got what looks like quite an interesting sequence of regions, which again, endpoints map to endpoints in nice ways. I've got a Markov partition. Not enough. Okay, Markov partition tells me what the dynamics is. It doesn't tell me the geometry of the dynamics. So can I do better? Well, the first thing is that in the wedges, if I take pre-images, I take this wedge B and take pre-images backwards, they sort of cycle, basically things are cycling around, so each of the smaller wedges around X star has a pre-image of B in it, and all points close to X star there have things that eventually go to B. And there's where it goes. So the line 0x star is really interesting. So suppose I'm on this straight line from A0 to X star. What happens if I iterate? Well, it goes to there. Then it goes to there. Goes on and on and on. Now from here, X star is fixed, remember. AK plus 1 goes here. So the next step is there. And now I've got to use both maps. A minus 1 there goes to A0. AK plus 2 goes to X star. And X star remains fixed. So the image is stretched twice completely across here. So on this line, I have an attractor. So I have an invariance. This line is actually under the nth iterate invariant. Okay, and the attractor is the whole line. Okay, I've stretched it across twice. Okay, it's expanded. Now I want to put those two things together. And basically, it's an idea that I did to prove a conjecture of Grussberger and Pekowski about a different sort of piecewise smooth map, which was proving that you had, although you had an attracting line which attracted almost everything, you actually had around that line a region with dense periodic orbits, and which was a topological attractor. So, and so basically what you're doing is you're now saying take anything, it will expand up and intersect the line. Once you're on the line, you can use the expansion on the line to get a neighborhood of this. And once you've got a neighborhood of that, you use the expansion around here to prove that everything gets filled in. Because once I've got a neighborhood of this, I've got a neighborhood of X star. By that wedge argument, that means the image of this goes to a bit here, 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 a bit here. So now I have a neighborhood of X star. X star is an unstable, in all directions, fixed point. So it will contain a neighborhood which expands out onto the whole of the right-hand bit. The image of the right-hand bit goes to the left-hand bit, and so I get everything. Okay, so that's, roughly speaking, the example. Right, so that was the Markov partition. Then I discovered that there are some wonderful theorems from the 1990s, which I've got on another slide I'm not going to put up because we haven't got enough time. So this is just typical of the way these sort of things, you do what you think is interesting, you sort of try to prove what's happening. So I was still not, so Tsujii was still saying, well, you know, okay, you've got countably many examples, but they're special. And they are. They're Markov partitions. Okay, so can you do better than that? So I went, you know, you just find things when you're looking on the literature, you find things. Turns out that in 1999 and 2000, a couple of amazing papers were being written by ergodic theorists about strong expansion. So particularly Buzzi, Tsujii, Gerhard Keller was involved, a number of people. And they wrote down conditions for expansion type results that give you n-dimensional attractors in n dimensions. And so I was able to take their results, modified a bit because there were some technical things, so you couldn't completely do them. It was fairly trivial, but it wasn't completely trivial. And the nice thing about that is it was robust. So we're back to this robust chaos thing. So, how much time do I? Oh, I do. Yeah, so let me just. So, Buzzi and Tsujii. So, this allowed me to do much better and to actually try to get back to the robust chaos type of idea. So the problem I guess I felt I was facing was, to begin with, we weren't even sure whether these things existed. So, do there exist fully two-dimensional attractors? So the Markov partition arguments allowed us to show that yes, there can be. What the work by Buzzi and Tsujii allowed me to do was to prove that there exist open parameter regions, and that means robust, such that, even better, if mu is less than 0, the map has a stable fixed point, and if mu is greater than 0, the map has an attractor of topological dimension 2. So actually, the picture that you saw earlier from the border collision normal form, where you have a stable fixed point going to a chaotic attractor, was actually for one of these, the quasi-one-dimensional attractors. But we can do the same thing in appropriate bits of parameter space for a fully two-dimensional attractor. Okay, and I guess, you know, the subtlety there is, I mean, what Tsujii was arguing was that, well, you perturb that a little bit, and surely, you know, you can, it will create a fractal structure or something like that. So, there is a technicality here, is that the results of their results depend crucially on the linearity. You're using the linearity to control various intersections. There's some nasty things that can happen if certain types of intersection of effectively lines in the two-dimensional case intersect in nasty ways. And the nice thing about the linear maps is that images of lines as lines, so you're talking about intersection of lines. In nonlinear maps, iterates of lines are curves, not lines. And of course, curves can start wrapping round and doing sort of nasty things. And so you lose that. So anyway, what I was able to do in a series of papers was prove, first of all, that that you could get these things on open sets, and then, if you like, this extra bit, which is that in terms of the bifurcations, you could get stable fixed point going to fully two-dimensional attractor. You can also do higher dimensions once you've got the Tsujii and Buzzi type of things. So there are open parameter regions of n-dimensional border collision normal form, such that if mu is less than 0, the map has a stable fixed point, and if mu is greater than 0, the map has an attractor of Hausdorff dimension n, so fractal dimension n, and typically this has topological dimension n. As you go from 2 to 3, there is this change in what the maths allows you to do. So you're able to show that you have some set that has full Hausdorff dimension. Typically, it's also got full topological dimension, but there may be particular points at which you don't have full topological dimension, but you have a fractal type structure with full Hausdorff dimension. So it's the dimension on the Cantor set. So that's nice. And I should say, at the moment, one of the things that I don't know is whether this is about techniques of proof or whether it's a real effect. So remember, when you're doing the maths, you're proving what you can prove, not what you can't prove. Okay, so it may be that you can get rid of the Hausdorff dimension part, and it may be that you can't. So, yeah. So I guess I'm about finished. So I think we're going to have a discussion. So I don't want to go in too much of this. I'm going to say bits of it before. Thank you. I'm going to say bits of it in the discussion. Challenges, lots of them. Okay, this is a really open area still. One question that we've been ignoring when we've been looking at the piecewise linear systems is the effect of the nonlinearity. Remember that the derivation of these things was always plus higher order terms. So when you stick with higher order terms, how does it change the picture? Again, avoiding lists, trying to sort of get some principles wherever possible. What level of description is appropriate? What's your problem? So depending on your problem, your answer is going to be different. Okay, you don't want to do, loads and loads and loads of detail if that's not relevant to the problem that you're looking at. So sort of trying to work out what question you want to ask of the system is important. Connection with flows has all sorts of interesting things. I mean, David showed you a bit of that where the maps comes in. And there's lots of more detailed questions. I think the whole higher dimensional issue for me is really interesting at the moment. And, it's really hard, but it's interesting. Okay, so that's me done. I think we have coffee, and then we have a discussion. Thank you. Oh, any questions? Well, we can have questions in